Ready, I will get this started.
Yeah.
Here we go then.
We're good? Okay, so has everybody got a copy? I've got extras if you don't. Okay, good. So this isn't everything that could be on a test because I don't think I could squeeze everything in an hour. It's more of an overview type thing, and it's more of things that I think make good open response type questions because I feel like that's where people feel most worried. Because when you see multiple choice stuff, you just see an answer, right? And you just got to recognize it. It's a little easier to retrieve something than it is to, or at least to recognize something than it is to entirely just pull it out on your own. So let's just look at this example here. This is sampling methods, right? So we talk about a lot of different sampling methods. The one we talk about the most is simple random samples. And that's kind of the one we're assuming when we do stuff in chapters 7, 8, 9, 10. But in the first place, we talk about a lot of sampling. And it's the chapter where you have to learn a lot of definitions and it's a lot of memory stuff. It is not the most exciting, but it's maybe the most important chapter because it allows you to recognize bad statistics, right? If you have a bad sample, everything that comes out of it, even with super fancy math, is worthless. And so there's this quote I like: garbage in, garbage out. If you don't have a good sample, everything else afterwards is worthless. So that we learn about that right now is very important. So this one has 5 different types of samples. Let's see, the city has 5 property classifications: single family homes, apartments, condominium, temporary housing, and retail property. Randomly select 10 residents from each category. Does anybody know what type of sample that is? Also eager to answer. Yes, right. Fantastic, Zarina. Random stratified. So I think that's B, right? Okay, good. And so then we say each property owner has a 5-digit ID number. Use a random number table to choose 40 numbers. If you're in the 1970s, now we just ask a machine to do it for us. And what's the answer for that? Oh, so that's a great idea. And I can kind of think I see why you would say that because there's this system to it, but it's a specific system that has its own name. So it's not the answer I would go with. Yeah, it's a simple random sample. That's right, Kimberly. It's basically like you're writing down their names on pieces of paper, throwing them in a hat, shaking it up, and pulling them out. That's what the random number table does for you, or what a machine will do for you if you ask it to give you a random sample. At the start of each week, survey every 10th person who arrives at the city park. What do we think? E. Yes, that is a system for doing it. That's very good. Randomly select 20 city blocks and survey all the residents in each block. Oh, very good. Okay, yes. And then have each firefighter survey 10 of his or her neighbors. What do we think that is? Yeah, that's A, that's convenience. Of those sample types, what's the one we like the least? Yeah, convenience, because it's worthless. It's easy, right? But the only thing a convenience sample will tell us is about the people in the sample, nothing else, right? Now, I find that what people get confused about most on sampling methods is the difference between stratified and which other one is kind of like that. Which one? Or maybe you don't get confused. That's even better. Is there another one that we sometimes get confused with stratified? Cluster. Yeah, right, because they're both grouping things. Does anyone know the difference? Like, when do we pick stratified? When is it a cluster? Like, relate that to the other one, though. I think maybe you have the right idea. So the way I think about it is when we're looking at the difference between cluster and strata, I think, well, what is, when you hear the word strata in another context, do we ever hear that word? Stratosphere, which is the different layers of the atmosphere, right? Or if, you're digging different strata of the earth. So it's these hierarchical levels, right? Whereas a cluster, I think a handful, right? It's not necessarily like kind of a category with a relationship. It's more of a, well, I'm going to go over here and grab some and go over here and grab some. And so when there's some order to it, I think more stratified. All right, so name and briefly describe the kinds of bias that might be present if the administration decides that instead of selecting people randomly, they'll just interview people about the new property tax at a fire station open house. So they announce they're having an open house, they invite people to come, and then they say, how do you feel about this? That could be biased, right? In what way? And do we have a name for that? Okay. Keep going. Whoever said it. So just tell me kind of what way this is going to go. Don't erase anything. You're saying very smart things. It's great. Yeah. Yeah. So I think anytime you do like an open house, anyone could come, right? And they're more likely to come if they have strong opinions one way or the other. Most people maybe just don't care or don't read the newspaper or whatever it is, right? And so you could see this as a convenient sample, right? That's who shows up, so we'll take it. We could also say there's likely going to be undercoverage. In both, I think we could talk about voluntary response bias. Anybody remember what voluntary response bias means? Yeah. Yeah. So, and the word volunteer is very confusing because anytime you're working with humans, with people, you're not forcing them to do anything because that would be unethical, right? So they're always going to be there voluntarily. But the difference when we say a voluntary response is we're like, hey, come answer these questions if you want to. We're not picking individuals and asking them to do it specifically. We just like put up a sign or something, and it's very much they see it and they're like, I'm bored, or I'm lonely, or I care about this thing, right? I said undercoverage up here, and maybe I glossed over it too quickly. What does undercoverage mean in this? Anytime, really. We want a sample that's representative of the population for sure. One of the ways we try to get to that is with random samples. We have this idea of sample frames. We have the population, we have the sample frame, and we have the sample, right? And if you remember, the sample frame is the group that we really can pull the sample from. Ideally, it would match the population. Sometimes it's smaller. So if we're doing a big study and we're calling people, the sample frame is going to be people with phones, right? And so if we cared about a large portion of people who wouldn't have phones, undercoverage would be a big issue. In this case, if we're just doing an open house, there's going to be a lot of people who don't show up. Those people's responses are probably going to be part of that population feeling. And so there's undercoverage for that reason. All right, good. Let's talk about this next one. Max wants to start a farm to grow mussels, as you do. He needs to determine the best environment for growing them. He's going to try 2 different amounts of salt in the water. So he's changing the salinity and 3 different water temperatures. For his experiment, he has 18 aquariums, each with 20 mussels. He wants to see which environment produces the largest mussels. Is this an example of an experiment or an observational study? Yes, fantastic. It is experiment. But What's the difference between an experiment and an observational study? Yes, and we call those changes typically treatments. Yes, in an experiment, we apply a treatment. What do we do in an observational study? We observe, right? We watch, absolutely. That's it, right? We're not making those changes. We're writing them down. There aren't any questions about this, but some of those differences are important. If we were doing observational studies, we talk about two major types. We talk about, man, I have a sinus infection and it just makes my brain blank more than usual. Retro what? Retrospective observational studies. And what's the other one? Prospective observational studies. What's the difference between those two things? Yes, Connor. Exactly. The same way we look at these words in general, when we see retro, that's the past. That data exists, and we're grabbing it to look at it, right? Prospective means we are trying to figure something out. And we're like, hey, let's go get this data. Maybe we follow people for a number of years. And so those are both very helpful types of things. Now, this is an experiment, and as Lindsay said a second ago, it's because we are applying at least one treatment, maybe more. Explanatory variables here. What do we think? Yeah. So if we're talking about graphs, we typically put those on our like x-axis. We treat them as our independent variables. Sometimes there's one, sometimes there's more than one. What do we think here? Yes, fantastic. Salinity and temperature. Good. Now read through that again for a second and see if you can figure out how many treatments there will be. Usually if you can figure out how many, that's a long ways towards actually writing them down. Do we have anyone in Zoom?
Mhm.
Oh, good.
9.
Hi, Zoom people. Hey, Zoom, does anyone want to guess how many treatments there are?
Six.
6. Fantastic. Yes, who was that?
Andrew.
Andrew, wonderful. Good job. So Andrew's right. There are 6. And he may know what that is because there are 2 levels for salinity and 3 levels for temperature. Now, it didn't tell us what those are. So I'm just going to call the salinity levels low and high. And let's say temperature low, medium, and high. Those are the different values those variables can take. And so we want to look at each combination to describe our treatments. And so one treatment would be low salinity, low temperature. And then we just go through all of them. Low salinity, medium temperature. Low salinity, high temperature. High salinity, low temperature. High salinity, medium temperature. High salinity. Oh, high temperature. Right? Good. So you know what? It doesn't ask this on here, but how many of yes. Oh, that's actually what I was just gonna ask. You're so clever to beat me to it. What well, you keep going. So a control itself, we would see as a treatment. Like if you give a placebo, right? Well, sometimes it is. In this case, I wouldn't just leave those empty. What else could I do with them? It's a good idea. So we could just do this with 6 aquariums and just let the other 12 hang out. But what else could we do? Yeah. Yeah. So what could we do like that way? Shelby, right? Yeah. Well, if we have 18 and we're trying to divide it into 6 things, right? So what would be the absolutely each treatment is over 3 aquariums, right? So you just have a larger sample. Yeah. Yes, Michaela. That's exactly how I think about it. Yeah, absolutely. Yeah. Very good. Any other questions? All right. Well, identify the response variable. What's that? Yeah. Well, muscle, how do you measure muscle growth? Size. Yeah. So that's exactly what I would measure. Very good. Yeah. Um, muscle size.
Oh, Caitlin says muscle size.
Oh, fantastic, Caitlin. Yes, perfect. Um, describe an advantage to random assignment of treatment. Yeah. Okay. So anytime we talked about randomization, one of the things it can help with is reducing bias. So that's a great first thought. It's a great answer. Any other things we might consider? So random selection really helps with bias. When we're looking at random assignment here, I'm thinking of something a little bit more specific here. So you're talking about something that's blinded. In this situation, I don't think it makes sense for it to talk about blinding because, well, so you could, if we wanted to blind this experiment, we have single and double blind things, right? And for single blind, we typically talk about the subject not knowing what treatment they're getting, right? And I don't know much about muscles, but they probably don't know what's going on anyway. So, I mean, they probably are pretty blind to it. Are they smart? Does anyone, some of you are biology students. Okay, so we don't know. So I don't know. You could have whoever's taking care of the aquarium not know which is which. I mean, you could blind them if you wanted to. Let me, you know what? Let me just say what I want to hear and then we'll talk about it. It can reduce the effect of confounding variables. So way back in chapter 3, when we talk about regression, we talk about, correlation does not imply causation. When we first start talking about observational studies and experiments, one of the reasons why we like experiments is they can help show a causal link because you're controlling for things, right? Observational studies are harder to control for things. Prospective ones can indicate a causal link, but we really want experiments for that typically. So here, when I say to reduce the effect of confounding variables, let's say you go to the, I don't know, store where you buy mussels and you got to get them from a couple different places. Maybe one of them has a healthier supplier. And if you put all of those in a few aquariums, they might do better than one you get from your neighbor who has them as pets. I don't know, right? So, I mean, definitely their source could influence how they do overall. Like if you, it's spring and some of you plant flowers and vegetables, right? Where you get those starters makes a difference because some places they're more likely to die very quickly, depending on how they're started. And so I imagine the same is true for, you know, any delicate organism. Yeah, they go together. So the really good, a confounding variable, a lurking variable, we're talking a confounding variable. What does the word confound mean? Okay, honestly, the only time I can think of hearing it is like an old person in a cartoon saying confound it. It messes up, right? And so when we think lurking, we think hiding, right? And so that's a variable that's influencing things that we don't know about or we're not taking in consideration. The example I really like is, I think I put in the notes way back, is wrinkles and gray hair are highly correlated, right? But one isn't causing the other. There's a confounding variable there, which is age. Okay, good. Oh, okay, we're going to monkeys. Did I skip anything? Nope, okay. So 10 little monkeys were jumping on a bed. There is a 35% chance that one will fall off and bump his head. In the bedroom next door, 5 kangaroos were jumping on a bed. Being more adept at jumping, there is only a 20% chance that a kangaroo will fall off the bed. What are the chances that a monkey and a kangaroo will fall off the bed? So, chapter 5 is all about probability. And there are some things to learn there and understand there. And one is the word independent. Okay. And so, are these events independent is a very important question for us to be able to answer. Okay. And so, you know, if the monkeys and kangaroos are in different rooms, whatever the monkeys are doing is largely independent of what the kangaroos are doing, right? So we can assume a monkey falling or not falling isn't going to influence a kangaroo falling or not falling. I'm going to also say that about the animals in the same room. Whether one falls or not is going to be independent of the others. Okay, so having said that, let's see if we can answer these. What are the chances that a monkey and a kangaroo will fall off the bed? What do we think? How do we find it? Like, I don't expect you to spit out the answer. Yes, and that's why I talk about independence, right? Because when they're independent, it's super easy. You just multiply and you get the answer. And I think it's reasonable here to assume that they are. And so the probability of a monkey falling and kangaroo falling.
Andrew thinks it's 7%.
I have no idea. So let's see. I think Harley just a second ago said that is point. Well, what is the probability of a monkey falling? Okay, so that'd be 0.35 times 0.2. And you know what? That sounds, what did Andrew say?
7%.
That sounds perfect to me. That's very good.
Well done.
Yeah. Now, you know, the next question seems a little tougher, I think. What are the chances that a monkey will not fall off the bed? And the word not might make you think certain things. Yes. Fantastic. Yes, very good. So the way I would do that, remind me, what's your name? Ellie. Okay, yes. I would write probability of not falling is 1 minus. Now you said compliment Ellie. How would I write that? Yes. So here I would write maybe 1 minus P of fall, right? Perfect. So what would that be? What are we talking about here? Monkeys. Yes, very good. So 1 minus 0.35 equals 0.65. Very well done. If the monkeys enjoy this activity every night for an entire week, what are the chances that a monkey falls off the bed every one of the 7 nights? So there's only a 35% chance that one's going to do it each night. So how do we figure it out for every single night? What do we think? Yep. And we were able to do that because they're independent. So you're exactly right. I'm going to say 7 falls. That's the same as 0.35 times 0.35 times 0.35, 7 times, right? What's an easier way to write that? Absolutely 0.35 to the 7th power, which is going to be a pretty tiny number. Anybody want to tell me what that is?
Desiree says 0.00064.
Desiree, that is perfect. Thank you. Yes. So I mean, this is what you should expect. Monkeys are probably very good jumpers, I would think. Probably not careful, but very good. So very low chance of that happening every night. So these are all pretty much the same. I mean, remembering complement, that's important. What are the chances that if the monkeys jump every day for a week, that at least one will fall off the bed? And I think of these questions, that's the toughest one. For me, the key to solving that is when I see that word at least, one possibility jumps out at me. Does anyone know what that kind of keyword tips us off to make things easier? It is that word, yes. At least it's telling us to do what, Mikayla? Maybe. That's okay. Anybody? I bet someone on the internet knows. Someone on the internet always knows.
One minus 0.00064.
Oh, okay. So who said that? Okay, Andrew said 1 minus. It doesn't even matter what he's saying 1 minus. When he's saying 1 minus something, what are we talking about? Starts with a C. Yes, the complement, right? What a nice thing to say. So the word at least, think complement. So 1 minus, this is the same as, what does this say? At least one falls off. So the probability of at least one fall is the same as 1 minus the probability of. Now, I don't know that it would be that 0.00064 because the complement of at least one fall, what is the complement of at least one fall? In other words, it's not contained in at least one fall. So at least one fall could mean 1 fall, 2 falls, 3 falls, 4 falls, 5 falls, right? Up to 7. What's the one thing that's not included in that? What's the one thing that is the complement? Yes, that's it. No falls. Now, what I was just talking about is the longer way to do it, right? We could say the probability of 1 fall or 2 falls or 3 falls or 4 falls or 5 falls or 6 falls or 7 falls, right? And because they're ors, what would we do with those once we found them? We'd add them, right? Yeah, and so, but that's a lot of work. If we recognize we can do the complement, we're just calculating one thing. And so this is the same as 1 minus, now not falling 7 times, probability. What is the probability of not falling on one day? 65%, so 0.65 to the 7th power. And so that is going to be, what do we think? So what would it be when you do 1 minus 0.65 to the 7?
Desiree says 0.9509.
Yes, fantastic. Good.
Awesome.
Do it. Put it in your calculator. If you're not getting it, I'll come around and talk to you. Okay, I see a look of consternation. So what do we?
All right, while he's going around and doing that, is there anybody that has not registered and been checked in? Has everybody?
Oh, that would actually not be 0.9509, 0.95 wouldn't it? Yeah, so just a slight rounding error. That would actually be 0.951 if we were rounding down, or if we were rounding, sorry. Instead of remembering how to erase, I'm just going to write this. There we go. Good. Any other questions or comments about anything we talked about so far? Yes. All right, let's talk about people dying. The Titanic. Okay, so that was a big boat. Wait, we didn't? Oh, sorry. What are the chances that the kangaroo can jump 2 nights in a row with no one falling off the bed? How do we do that? Yes. Okay. So there is an 80% probability of falling. That's good. And so we would do, yeah. So that would be P of fall and fall. 0.8 squared is great. So that is what, 0.64? It is. So, oh, hang on. There's a 20% chance it'll fall. So I was just, listen, if you say something with confidence, I will believe it and I will just go straight with it. Oh, yeah, that is what it says, not falling. I just wrote it down here wrong. Not fall. Let's just give up grammar instead of erasing. Is that better? Are we all happy now? Yeah, because that's actually what it says. Made it 3/4 of the way reading correctly, and then I just lost it. Now we'll move on to the Titanic sinking. Lots of people died, and we are going to look at that by whether they were in first class, second class, third class, or part of the crew. Now, if we were to randomly choose a passenger off the big list of passengers and try to figure out if they died, the probability of it happening, well, that's actually what part A says. If, oh, no, we don't even care if they die. We just want to know what's the probability of a randomly chosen person being a crew member. How would I figure that out? I think that's fantastic. Yeah, it's how many crew out of how many people, right? And so what are those numbers? Okay, so 8A5, you're right, is the number of crew members divided by 2201. Very good. That's the total number of passengers. So just to make sure we know how to use a calculator, take me out to 4 decimals on that. What is that? I have a calculator right here, and it's only taken me 45 minutes to realize it. There it is. Yes, I agree. About 40%. Wow, that's a lot of crew members. It's a big boat, though, so. What is the probability that they were a second-class passenger that survived? Oh, so that one, there's 2 things we're talking about. The first one, we just wanted to know what's the probability they're a crew member. Now we're saying they survived and second class. And Desiree is saying second class alive divided by 2201. And the answer is, I don't know. I've got to read it again a couple times. Anytime we're doing problems, I would not recommend just looking at it once and writing down what your thought is. At least if you're me, because my thoughts are everywhere. So I have to do it a few times. I have to read it a few times, particularly if I'm nervous on a test, right? And so they were a second-class passenger that survived. So the number of second-class passengers is 285. Is that what I'm going to use? And so I think Desiree's already answered for us. I think she's saying it's about 5%, and I bet that's right. You all are saying, no, we're not going to use 285. Why is that? Good, because some of those are alive, some of those are dead. What number do we want to use? Yes, fantastic. And that's 118. So 118 out of it's a good question. What's the bottom number? What do we have a consensus? Desiree thinks it's the total 2201, 2201. Alana, what do you think? You think the same thing? Fantastic. I also think it's the same thing. Yeah. 2201. Very good. And so let's see if the calculator helps me with that. And I get the same number that Desiree did. And I think that is it.
You got it.
There we go. Yeah. Yeah. So that proportion is as a decimal. If you want it as a percent, you multiply by 100, get 5.36%. Now, chapter 6, we talk about continuous probability distributions a lot. That's where we're talking about those normal curves, and we're using either a table or a calculator. There's a little bit of talk about discrete probability distribution. And so that's why I wanted to start looking off here by making one. Here, I want to look at rolling two dice, right? And so if you roll 2 dice and it says, look at the difference. What does difference mean in math words? Yeah, so we're rolling through 2 die and we're subtracting the values we get. So if both of them land on 1 and we subtract, what do we get? 0. Okay. What's the smallest number if you roll 2 die and subtract that you could get? 0. Okay. Yeah. So let's do this. Let's write x and p of x. And let's write down all those possibilities. So it could be 0. What's the biggest difference you could get? I guess I'd think about the highest value subtracting the smallest value, right? Which would be what? Yeah, 6 minus 1 is 5, right? And so if you look at those and start subtracting, you'll see it's everything in between 0 to 5, right? There we go. Yes, Connor. Yeah, so I'm taking just the absolute difference. So like if you said 1 minus 6, it'd be -5, right? I'm just taking that to be 5 from the 6 minus 1. Does that make sense? No. Okay, so do this for me. Pick two values that can come from a die and give me a number smaller than 0. Okay, 3 minus 2 is 1. Does that make sense? So we're always just going to take the convention of bigger minus smaller. You could do a separate problem like you're doing, and that would be great. I'm going to do the easy thing. Now, we're going to look at the probability of each of those, and it helps that we have, what is this thing called where we look at all these possibilities? Starts with an S. Yes, Kimberly, very good. Sample space. That's the sample space, right? And it's how many things are in that sample space? 36, right? And it's not too hard to figure out why, because 6 possibilities, 6 possibilities, 6 times 6 is 36, right? Now, how many of those things are going to give us a 0 if we subtract? Yeah, where are those 6? Yes, fantastic. It's where they're the same. It's the diagonal there. And so that is, you said 6 things, right? Out of 36. Perfect. All right. Well, you know, what's one thing that will give us a difference of 1? Okay. 2 and 1. What'd you say? 3 and 4. 3 and 4. 4 and 5. 5 and 6. 2 and 3. Kind of a diagonal of its own there, right? How many is that? Good. So 5 out of 36. And then we look for the 2s, right? And so 3 and 1, which I bet I can erase. So this one would work. 3 and 1, 4 and 2, 5 and 3, 6 and 4. Is that all of them? I don't think it is. Does anybody see one I've missed? Well, so you're right, because of these over here, right? That would, if you subtract, give you those negative ones. And so your idea is way smarter than what I'm doing, because I'm just looking at something, and you used your reasoning ability to come up with that. That's very good. So how many is that? Oh, no, I'm talking about the 2s here. Yeah, I don't think I missed any 1s. Yeah, 8 out of 36. Okay, and then we're going to do 3, 4, and 5. So you know what? Go ahead and try to do 3 right now, and then I'll just jot out the other ones if we feel okay about that. And if you're confused, raise your hand and I'll come help you find them. So right now, oh, I did. I did. Yeah, so I am blind. Harley tried to save me. Kylie did. When we were doing the ones, I even drew lines to all of them and then only counted half of them for some reasons, right? So 1, 1, 1, 1, 1. There's 10 of those, and I wrote 5. There we go. Okay. Now, what about the 3s? Does anyone come up with a number? Someone said yeah. 6 over 36. I have no idea. Let's see. Any other numbers? Everyone thinks 6? All right, let's see what I get here. So I'm looking for 3, so 4 and 1. 5 and 2. 6 and 3. That's 3 things. And yeah, Desiree's got them listed there. She's also getting the exact same thing. So we do in fact get, you're right, Lindsay and Desiree, 6 out of 36. Very good. And then we do the 4s. So the 4s, I mean, there's only 2 more. I'll just go ahead and work those out too, or find them. So 4, 6, and 2. And 2 and 6. Is there anything else? That have a difference of 4? Yeah, absolutely. 5 and 1 and 1 and 5. So how many is that? Yeah, very good. 4 out of 36. And then 5, there's going to be fewer ways to do that. Yeah, so 1 and 6 and 6 and 1. That's it. 2 out of 36. Now, the instructions say to give decimals for each of those. I don't really feel like doing that because I want to move on to the next problem. But are we okay finding decimals for each of those? Yeah, right. You just do like 6 out of 36. You'd be like, all right, 6 divided by 36. That is 0.1667, right? Let's do some just regular questions here. If I add all those up, what should it equal? Yes, 100%. Very good. Every single probability is between 0 and 1. They have to add up to be 100%, or in this case, 1, right? Which is the same as 100%. Do they? I don't know. Let's see. 6 and 10, that's 16, and 8, that's 24, and another 6, that's 30. That's 36 out of 36. That's 1. That's perfect. If you wrote the decimals out to 4 decimal places and added them out, well, I mean, you might be off by 0.000 something, right? And that's okay. But if you're off by 0.3, that's huge. That's something you should be concerned about. And so it's an extra way to check yourself. Find the mean of the probability distribution. Now, the way we typically find the mean or the average is we add them all up and we divide by how many, right? And that works great when they're all equally likely. But otherwise, we do what's like a weighted mean, right? Like if you're finding your grade and different categories are weighted differently, when things are more likely, that's going to be weighted more heavily than things that are less likely. So does anybody remember how to find this? Yes, Ella. Yes, and then what do you do with those? Yeah, fantastic. If we want fancy math to say that, we say what is this? Sigma or sum of x, p of x. Very good. And so for us, that's going to be 0 times 6 over 36 plus 1 times 10 over 36 plus 8 times, no, I'm sorry, plus 2 times 8 over 36 plus 3 times 6 over 36 plus 4 times 4 over 36 plus 5 times 2 over 36. which I'm going to actually give a nice value for that. So you put these all in. The 0 I can just not put because it's just 0, so I can be lazy there. And I can say 10 divided by 36 plus 2 times 8 divided by 36 plus 3 times 6 divided by 36 plus 4 times 4 divided by 36 plus 5 times 2 divided by 36. And that's going to give me 1.9444, which makes sense that it would be a smaller number because look how much heavier they're weighted on this side. When we get all the way out to 5, there's only 2 of those that are possible.
Do we not divide?
Okay, so Desiree said, do we not divide? And that is a brilliant question. We have divided. If you wanted to, we could actually look at this as adding 0 times 6 plus 1 times 10 plus 2 times 8 plus 3 times 6 plus 4 times 4 plus 5 times 2, and then divide everything by 36, right? We just divided at each individual step. And that's actually how we find any mean. We think of it as an easier way when things aren't weighted because we say, okay, just divide by how many without doing the weighted because they're all weighted at 1. But you could always add each of them up divided by the total number. And since it's a common denominator, you can see very quickly, oh, it's the same thing. So that's a very good question, Desiree. Does that make sense, the answer? Oh, yeah, it already made sense. Very good. All right, now we are moving on to continuous probability distributions, the ones that we use a lot more in this class. So this is going to be fundamental going forward in chapter 7, which you probably already started, chapter 8, chapter 9, chapter 10. Okay, so bell curve is what some people call it. Nice normal curve, looks like a bell. And we'll talk about how to use our calculator for these. Copy machines. A manufacturer claims that lifespans for their copy machines in months can be described by a normal model with, oh, I love this notation, which is why I wrote it this way here. It's such a nice compact thing because all the time we're assaulted with just so much information. And that gives you so much information in a tiny space. It's easy to absorb. What does the 42 mean? Yes, it's the mean. Very good. What does the 2 or what does the 7 mean? Fantastic, right? And so if I'm trying to put this on my graph, where would the 42 go? Yes, and the reason for that is if you're looking at a graph and you want to figure out where the median and the mean are, the median is if you were painting it and you started on the left, the median is where you would have used half the paint. The mean is where if you like cut it out on foam board and you tried to balance it on your finger, that's where the mean would be. Now, if it's symmetric and unimodal, they're the same place. The mean, median, and mode are all right there. So that's 42. And then the standard deviation, it's not uncommon to write out 3 standard deviations like we did with our empirical rule. So I would go within 3 standard deviations of the mean. If you want to be really careful with that, the first standard deviation happens at the inflection point. And what that means is you see how you can't see my hands here. So do you see here, if you can see where I'm covering over it, you see how it's this kind of facing down cup? And then it changes to a facing up. That point where it changes is called a point of inflection, and that's where the first standard deviation is. You don't have to be all that accurate. For some reason, it just makes me feel better to know that. And so it's easier for me that way. Otherwise, it looks all weird when I kind of guess at it. And so I go over that amount. That would be what, 49? And if I subtract 7, that's harder. What's that going to be? Yeah, 35. And so I do that again a couple times, same distance. From 49, it's going to be 56, and then all the way out to 63. And then over here, let's see, right around there to be 28 and 21. Now, question A, I'm going to give you a huge hint. If you remember the empirical rule, which some people call the 68, 95, 99.7 rule, it makes that problem a lot easier. Can anyone read that and maybe tell me what they think the answer is? Okay, well, think empirical rule, think 95%. That's going to tell you. It's between what two numbers? All right, so Tyler said that with confidence, so I'm going to write it down and I'll actually look at it. So why does Tyler say 2856? Because that's 2 standard deviations from the mean, right? And so that we know about 95% of the results are going to fall in between there. Now, saying that exactly that many is going to happen is silly. It's not likely to happen because we know there's variation between samples, right? But it's not a crazy idea that it would be close to the values that were being quoted there. Of course, you know, the salesman would probably be focusing on the 56 more than the 28. What percent of the copiers are expected to fail before 36 months? Yes. Yes. We could do this without it telling us specifically 95%. I personally think it would be friendlier to say 68, 95, or 99.7% because it's so direct. Don't let me forget, because I am super absent-minded. We can pull back to that right at the end, and I can show you how to do it. It's just a little bit more involved. It'll just make more sense after we do these other ones. It's a very, very good question. So, what percent of the copiers are expected to fail before 36 months? Yes. Yeah, I'll even write them down. 68, 95, 99.7. Now, anytime you're doing a problem involving a normal curve, I would strongly recommend you draw a picture. If you're in my class, it might be part of how it's graded. So make sure you're getting a picture in there every time. And so for this one, it says 36 months. 36 months is like right here. And you know, honestly, part of the reason I love the empirical rule is it lets me ballpark an answer so fast without looking at anything else. Now, immediately, because it's left of the mean, I know my answer is going to be less than 50%, right? That's like pretty close to 1 standard deviation though, right? And so 1 standard deviation, that middle 68%, how much would that leave in the tails? $100 minus 68 would be 32, right? Which, because it's symmetric, would be half in each tail. So that would be 16%. So I'm probably going to get an answer a little bit bigger than 16% because that doesn't quite go down to 1 standard deviation, right? Okay, so let's use a calculator to find it. I use distribution right here, D-I-S-T-R. And you can't see where my pen is right now, but it's next to the arrows and it's that vars button. So I hit second, distribution. And which option am I going to use most of the time? I'm going to use option 2, normal CDF. The C stands for cumulative, so it's like all that stuff before it too. And so I pick that option, and on most of them, it'll actually ask you specifically what is your lower bound, what is your upper bound, what is your mean, and what is your standard deviation. If you have one like this one where it just gives you the normal CDF command, then you need to remember it goes, and I'll write this down, normal CDF, and it's lower bound, upper bound, mean, standard deviation. And honestly, if I'm using my calculator to calculate something on a test, I would probably write down what command I used in case my fingers slipped. I could show that I still understood generally what was happening. And so when I do this for this problem, I'm going to put in what for my lower bound. This is a little tricky. Yes, I would put in negative. So the theoretical model stretches to negative infinity. And our calculators don't have a negative infinity button. So we just use a really, really, really tiny number. And as long as you go several standard deviations below the mean, you're going to be fine, because pretty quickly it becomes relatively accurate the further out you go. I'm usually lazy and just say super far, -10 to the 99th. That's negative 0.0000099 times, right? So it's just tiny and it's fast to type. And so then I say my upper bound for this one is what number? Yes, 36. Very good. And the picture shows that very nicely, right? And then the mean is 42. And then the standard deviation we said was 7. That's how I would find the area to the left anytime. And so I hit enter and I get that value. 0.1957. Now, if I was writing this on a test, I would actually be more specific than lower bound, upper bound, and say what those actually are. I wrote them that way so you would know the notation. So we just said we put in the calculator negative 10 to the 99th, 36, 42, 7. So about 20%. Now, go ahead and try to draw a picture for C. Just draw your little normal distribution. Try to throw a number. Oh, yes, I've got a question. Yes. Okay, yes, if you have any calculator issue right now while everybody's trying to draw, raise your hand. That's true for online too. Any other? Like, you know. Yeah. So what do you think? So it's what we're talking about. All right, so Hal asked a wonderful question, which made me realize I wasn't being very polite here. Even though I didn't give myself a lot of space, I shouldn't just put a number out in the middle of nowhere. I should say what that number represents, right? And so I'm going to say P of what? What do we think? X is less than 36. That look of disgust is fantastic. So let's start this one that way. P of X. What do we think? Greater than what? Yeah. Now I'm going to do this. I'm going to use my same picture here because I can be lazy. You should draw out a separate one. 57's right here. So it's going to look like this. Now, at minimum, when you're drawing your picture, which I can draw a little one here. I would put the mean and the value you're looking at. At minimum, I would do that. Okay. So whether you have a really nice picture like that or kind of a weird picture like that, the bottom one, you're fine. So this is equal to Now, when I'm doing the area to the right, is that 57 the lower bound or the upper bound? It is the lower bound. That's exactly right. So it's going to be the first number I put. So I'm going to do normal, CDF, and 57. Now, has anyone ballparked this using the empirical rule? Yeah. Oh, yes. Very good. What'd you get, Emily? Okay. Mm-hmm. Mm-hmm. Yeah. That's fantastic. Yeah. So were you raising your hand? Did you have a different estimate? Okay. So you could do that. You can actually even make it smaller. It doesn't matter. Yours was so good that you would know if you got a silly answer. And to me, that's the most important thing when I try to ballpark an answer. On that one, the 95% you said is perfect. Now that extra 5% would be split between two tails. So you could actually say it's going to be, like 2.5%, right? Or a little less. So very, very good thinking. So 57. Now the upper bound, how far out does that stretch? Yes, you're right. Infinity. That's good, McCullough. So what's a good number to substitute in for infinity? Okay, yeah, 10 to the 99. That's very good. I like that. That's what I do all the time too. So then what comes after that? What do we put after the upper bound? Yeah, mean, which is what? Yeah, and then perfect. So look, this is how to find the area to the left. This is how to find the area to the right. So the calculator's super quick. And so I would hit second distribution, normal CDF. My lower bound, we said 57. 10 to the 99th power. 42. 7. And I get that that's about 0.0161 to 4 decimal places. We feel okay about that? All right. Now, that third or fourth question, part D, seems out of nowhere, I think. How is that related to what we've done? How is it different? Yes. So it's actually using a word we haven't seen for a while. So when we talked about quartiles, that was back in chapter 2, right? When we talked about like IQR and things like that. It would help us if we remembered why they were named quartiles. Yeah, quarter, right? Which is like, so 3/4 is 75%. So it's saying where's the 75th percentile, right? So now that we understand better what it means, maybe you understood that to begin with, how do we find it? Well, or let's not even jump to that. How is that related to what we've been doing? Is it exactly the same as we've been doing, or is it? But let's not even worry about the calculator in terms of like what it means. I'm getting an answer of 49, and I don't know. What does that mean? Oh, I don't even want the answer. I just want to know what it means. Like, how is this related to what we're doing? Are we still finding an area? Are we still, what are we doing? Oh, yes, very good. So in the other ones, we're finding the area under a curve that we're shading, right? This one, the area is already given to you, so it's backwards, right? What's the math word for backwards? Yes. And so this is where we use that other function, right? And so let me draw a picture here. So 75th percentile, we know 42 is 50th percentile. So someone said 49. Now 49, I honestly don't know. I know one standard deviation gives me that middle 68%, which means if I cut that in half, 68% divided by 2 is 34%, right? And so if I went 34% above the 50th percentile, that'd be like the 84th percentile. So 49 is actually a very reasonable estimate for that. Yeah. Harley, did you have a? Mhm. Okay, so that is one of those things. So let me draw this really quick. So everything you just said was brilliant. So we want that area to be 0.75. Now, Harley said, she said something and then she says, I don't think it'll work because of this. And they're both very smart. So she said, well, 50th percentile is 42. So if I cut that in half, it's 21. I add 21 to that, right? And so if this was rectangular, where everything is equally likely, you could do that kind of thing. But the further we get from the middle, the less likely it is, the lower the curve is. That's why we can't do the math that way. Very smart idea. And you recognize the empirical rule didn't work that way, so you knew it probably wouldn't work. That's perfect. So we said we're going to use a different command, normal, I'm sorry, second distribution. And you all supplied the normal, right? The inverse normal. So what numbers am I going to put in? It tells me area, mean, standard deviation. What do I put in? Okay, so I'm not sure who's asking the question, but it says, isn't the third quartile the same as one standard deviation above the mean? And it is not the same. They're both ways of measuring variability, but they aren't going to give the same values, typically. So what area am I working with on this one? Okay, 0.75. What's the mean? Okay, 42. What's the standard deviation? 7. Guess what the answer is. Just give it your own guess right now. What's a guess? I mean, something bigger than 42, right? Because when I picture it to the right, that's a guess. That's very specific. Yeah, 46.72 is what I would get for that too. So 46.72 months. Now, earlier, someone asked, could I have done this first problem without the empirical rule if it was some weird percentage? And the answer is yes. And this is actually how you could do it with the normal inverse, but it's a little messy. Okay. So like if I wanted to find that middle 95%, and I'll use my eraser here, and you can kind of pretend I'm not talking for a second if you want, if this is a little scary. If I wanted this number and I said, okay, 95% here, I could find these two values by looking at the area in the tails. How much area would be in this tail right here? If 95 is in the middle. 2.5%, exactly. And so I could find the X value like we did right here for the 0.25 area. In fact, I'll do that. Second distribution, normal inverse, 0.025 for 2.5%, 42.7, and it's 28.28. The empirical rule told us 28. Does that make sense, the question you were asking earlier? That was a super smart question, and we're going to do things like that later on. All right, so I still went over on time, a little better than last time. I'll try to rope it in a little more next time. If you have questions, whether you are in my class or someone else's class, you are free to come to my office hours. If you aren't aware of what they are, if you just go to the website, it tells you. But mine are Monday, Wednesday, Friday from 11:30 to 12:30, Tuesday, Thursday from 9:30 to 10:30, others by appointment. And my Thursday office hours this week are canceled, so sorry. Otherwise, we're good though. And you can come ask me questions right now. Hey, we're answering all the questions. How you doing? What is